Good morning, class. My name is Akarsh Naik, and I'm working with my partner Ryan Hochstein, and we'd like to present to you our final project on ocean thermal energy conversion. There were many different motivations for choosing ocean thermal energy conversion, or OTEC, as our project. The main one is to meet the growing demands of energy security that the world is going to face in the next couple years. Uh, we also want to do this in a clean and renewable fashion. Another upside to OTEC systems is that they have desalination capability that can address water scarcity in tropical regions. And on top of that, it's a pretty underdeveloped technology, so we want to develop that and maybe even develop some jobs alongside developing this technology. Here you can see how OTEC systems compare against conventional energy systems. In areas like the energy resource and the environmental impact, OTEC systems are much better, they're much cleaner, they have a larger resource to pull from. But in areas like energy output, efficiency, and technology, OTEC systems are underdeveloped, they're not very well researched, so their efficiencies are lower, they require special components and special construction. However, with their efficiency being lower, they still do pull from a much more abundant resource than really any other conventional energy system. So that negative is a little underweighted for that reason. We also conducted a location analysis around the world of where an OTEC system best thrives. What you're really looking for is a large temperature gradient between certain levels in the ocean. We chose a depth of 10 meters to 1,000 meters to have a gradient of around 20 degrees Celsius. That's the average that we're looking for that makes a location optimal for an OTEC system, which gives you locations like India, Japan, French Polynesia, Hawaii, and other equatorial countries as best locations for an OTEC system. The overall goal of this project was to design an OTEC plant that is capable of producing 1,000 liters a day of desalinated water. It should have a positive network, should have a capital cost of less than $1 million, and a first law efficiency of above 1%. The approach we took in this was analyzing a system a little similar to a Rankine cycle. The overall system we first analyzed had two pumps, a boiler, and a condenser. We then designed the boiler and the condenser independently, integrated it back into the system by inputting the heating and cooling loads that we had determined. We then used UA-LMTD to determine the dimensions of the heat exchangers, and then from there we optimized to maximize our efficiency and decrease our size to limit cost of our materials. We explored several design options before settling in on one. We explored a closed system that uses a different working fluid other than seawater through a closed loop. This can't produce desalinated water. We explored an open system that does use seawater with a vacuum pump to lower the boiling temperature. We explored solar boiling for seawater. We explored boiling through a thermal oil heated through solar energy. And we also explored a recirculation method to not waste some of the heated water at the end of the cycle. Here you can see some of the assumptions we used in our design process. We assumed that our system operates under steady state. We assumed that heat loss is negligible across the condenser, friction pressure loss is negligible across the whole system, that kinetic and potential energy change is negligible between our boiler inlet and our condenser outlet. We also assume that our boiler completely separates salt from seawater. Our vapor is assumed to be saturated at the outlet of the boiler, and our liquids assumed to be saturated at the outlet of the condenser. Again, though we were hoping to output 1,000 liters a day of desalinated water and 10 kilowatts of work from our turbine. And with this and using UA-LMTD methods, we were able to design our boiler and condenser and their dimensions for construction. After comparing different configurations for the OTEC system, we decided on a hybrid system that uses solar energy to heat up a thermal oil to boil water through a turbine, and then that produces work and gives us desalinated water as we intended. Here you can see a TS and pH diagram produced by our final values of the model. Before deciding to use a hybrid system with a thermal oil, we tried to create a parabolic solar collector that boils seawater itself. However, due to its high specific heat, we realized that you would need a parabolic solar collector with an area of almost 600 square feet, which is just too large and too costly to manufacture and maintain over a long period of time. So after deciding to use a thermal oil and a hybrid system for our OTEC system, we had to determine what thermal oil we're going to use, the size of our parabolic solar collector, and the dimensions of the heat exchanger using UA LMTD methods. Through this analysis, we used given values from E's and the values we were able to develop from our initial simple analysis for our proposal. So we then had to determine what temperatures we're going to keep our oil at and operate it at. We decided to make these predetermined in accordance with how a concentric counterflow heat exchanger works. So we used a cold fluid temperature of 120 degrees at the inlet, 150 degrees at the outlet, and a hot fluid temperature of 250 degrees at the inlet and 200 degrees at the outlet, which gave us the following Q, LMTD, and UA values. By determining the temperatures of our hot and cold fluids, we were able to pair this with standard diameters of our inner tube, outer tube, thickness of our pipe, and the material of our pipe. We were then able to find Reynolds number, Prandtl number, and Nusselt number for both fluids to determine the heat transfer coefficient. And then using a resistance network, we determined a U value of 140 watts per meter squared Celsius, which falls in line with previously determined theoretical values. This all gives us a length of 4.737 meters for our heat exchanger. After determining the dimensions of our heat exchanger, we were then able to confirm that our oil temperatures are accurate and in the range, which allows us to start constructing our parabolic solar collector. Through the math you see on the slide, we determined that we need an incident area of 10.92 meters squared to heat up our oil from 200 to 250 degrees Celsius. Knowing we need this 10.92 meters squared of incident area, we used certain parameters such as keeping our heating tube 0.5 meters above the vertex and having a width of our parabolic dish of 2 meters to derive a characteristic equation of our parabola of y equals 1/2 x squared. And this allowed us to then determine that we need a length of 6.884 meters for that characteristic dish parabola, and which gives us also an arc length of that dish of 2.296 meters. In this analysis, we used a reflection factor of 0.9 of loss from the mirror to our receiver.
Now moving on to the condensing heat exchanger design. Since we have an open cycle OTEC system, the heat exchange will be from water to water, and so a shell and tube configuration is chosen. Here we're going to be using the UA-LMTD method, where we're going to be initially assuming our close approach temperatures and subcooling temperatures, and later fixing our UA values to design the heat exchanger. First, fluid properties at each state are determined via EES. This means we'll be finding our viscosity, specific heat capacity, density, thermal conductivity, as well as our dimensionless numbers and friction factors for each state. As mentioned, the close approach temperatures and subcooling temperatures were both assumed to be 3 degrees Celsius. Then our friction factors were calculated either using the Darcy or Blasius friction factor equations, depending on whether the flow is laminar or turbulent. The Reynolds number for each state is calculated, and the only laminar state is state 7. However, these Reynolds numbers will have to be continuously monitored to ensure that we're using the correct correlations for the Nusselt numbers. To determine the convective heat coefficient at each state, the Nusselt number must be calculated. For the shell side, the Zukauskis correlation for cross-flow over inline tubes is used, and that correlation is shown below. For the tube side, the water enters as a two-phase mixture, and so we use the Dobson and Choto correlation for film condensation in radial systems to find the Nusselt number. This is shown below. We must also find the surface temperature of the wall and H'(Fg) for this correlation. Finally, for the tube side, once the water is condensed to a liquid for states 5 and 6, we use the Nielsenski equation to find the Nusselt number for turbulent flow in a smooth pipe with a Reynolds number of less than 10,000. At each state, our convective heat transfer coefficient is found from the Nusselt number by dividing it by the thermal conductivity times the hydraulic diameter, and we have to make sure that each of our convective heat transfer coefficients are on the correct order of magnitude, and we verify that they are, meaning we can move forward with our analysis. We next utilize the UA-LMTD method to find the necessary heat exchange surface area. To do this, we must find the U values from the total thermal resistance, which includes the conduction across the tube wall, the fouling from the seawater, and the convective heat transfer from the fluids on the inside and outside of the tubes and shell. Once the overall heat transfer coefficient U is found for each heat exchanger, we can use the LMTD method. The LMTD method is used by finding the counterflow LMTD formula and adjusting this based off of the shell and tube heat exchanger correction factor for a two-pass heat exchanger. We find our correction factor on the chart below, and for the condensing heat exchanger, it will be 1. However, for the subcooling heat exchanger, it will be somewhere between 0.9 and 1. Several relations are made to determine the condensing and subcooling loads, as well as our UA values, by using the Q equals UA LMTD formula, as well as our Q equals m dot Cp delta T formula. Finally, the UA values for each heat exchangers are fixed, and the heat exchanger load is also fixed. This means we can release the close approach temperature, subcooling temperature, and turbine work. The heat exchange area for the condensing heat exchanger is 5.1 meters squared, and 0.04 meters squared for the subcooling section. We will initially assume geometries for our heat exchanger, but later this will be optimized in our parametric analysis. So the inner tube diameter was assumed to be a standard 0.25 inches with a wall thickness of 0.02 inches, although this will both be optimized later. The heat exchanger is designed with 2 passes, and the number of tubes is initially set as 24, but again, this will be optimized in our parametric analysis. Also, the pitch is assumed to be 1.25 for a triangular tube configuration. Similar heat exchangers to this can be found on McMaster-Carr for less than $5,000, showing that this will fit into our budget restraints for the system. Finally, we find our pressure drop across the heat exchanger by calculating our major and minor losses. Our major losses are going to be our frictional losses, and minor losses are going to be from the entrance, exit, and bins of the heat exchanger. We will take these pressure losses into account when we're calculating our net work, as this will increase the work input from the warm and cold water pumps. Next, we performed several parametric analyses with our heat exchanger geometries. Here we see that as the tube diameter increases, the net work also increases, but so does the total area of the heat exchanger, and that is the same for the number of tubes. We found that the optimal number of tubes is around 50, and the optimal tube inner diameter is about 0.01 meters. After optimization, we came to the following chosen design. We will utilize a 2-pass shell and tube heat exchanger with 50 tubes with a 0.01 meters inner pipe diameter and a triangular tube configuration. This total heat exchanger length will be about 4 meters. Our counterflow concentric heat exchanger is our boiler. This will have a 0.03 meter outer diameter and a 0.025 meter inner diameter. It will also have 0.0025 meter thickness of its copper pipes. This heat exchanger will be about 4.7 meters in length. Finally, we have our parabolic solar collector, which will be 2 meters wide and about 7 meters in length. It will also have a 2.3 meter arc length of its dish, and it will have a 0.5 meters of height of the glass collectors above the vertex. Finally, we can analyze our system performance. Our first law efficiency is 1.169%, and our second law efficiency is 2.275%. While these efficiencies are quite low, for OTEC systems, they're actually within the normal ranges. Our net work is 0.659 kilowatts, meaning we are energy positive, which met our goal. Finally, we produce 957.3 liters of desalinated water per day, which falls slightly under our goal of 1,000 liters per day. In completing this project, we found that ocean thermal energy conversion has a high potential for energy production and for freshwater production due to the near infinite resource bank, which is the ocean. However, these systems are incredibly inefficient, so any efficiency improvements go a long way. Some of these systems might be more suitable for smaller scale levels due to their capabilities of small scale desalination and energy production. We also learned about using thermal oils in our solar collector as a heat exchanger for water to transform the inaccessible energy to working fluid. We recommend that ocean thermal energy conversion systems utilize solar energy instead of vacuum pumps so that they can improve efficiency and make use of the available energy. Finally, here are the references we use for our project.